Welcome to our video on how a hydrogen bomb works. It's a captivating yet intimidating topic given the substantial strength and possible devastation these instruments wield. However, the scientific theory behind it is genuinely captivating. So, let's get started without further delay and delve into the intricate universe of thermonuclear weapons, more commonly known as hydrogen bombs. Today, we'll be taking a close look at the detailed scientific process behind this mighty armament. In our previous scene, we introduced the concept of a hydrogen bomb, a thermonuclear weapon with immense destructive power. But how does it function? What are the principles behind this awe-inspiring force? A hydrogen bomb, also referred to as a thermonuclear bomb, operates on the principle of nuclear fusion. It's the same process that powers our sun, creating a vast amount of energy through the fusion of lighter elements into heavier ones. In the case of a hydrogen bomb, this involves the fusion of hydrogen isotopes, typically deuterium and tritium. This fusion process releases an enormous amount of energy, far greater than the energy produced by a simple fission reaction. The energy is released in the form of kinetic energy, heat, and radiation, resulting in an incredibly powerful explosion. The goal of this video is to demystify the complex process of how a hydrogen bomb works, from the initial stages of fission to the final devastating fusion. So let's dive deeper into the science behind it in the next scene. In this scene, we'll delve deeper into the role of the fission bomb in a hydrogen bomb. As we've mentioned, the process begins with a fission bomb, similar to the atomic bombs used during World War II. But why is it necessary? Well, the fission bomb is the spark that sets off the whole chain reaction. It creates the conditions necessary for triggering fusion reactions. When the fission bomb is detonated, it releases a tremendous amount of energy in the form of heat and radiation. This extreme heat and radiation cause the hydrogen isotopes in the secondary stage to heat up and compress, reaching temperatures and pressures high enough to start the process of nuclear fusion. Remember, fusion is a process that requires extreme conditions to occur, the same conditions found in the core of our sun. By using a fission bomb, a hydrogen bomb is effectively creating its own mini-sun on Earth. This is a critical step in the process, and without the fission bomb to kickstart the reaction, a hydrogen bomb would simply not work. But how does this fission bomb lead to the fusion stage? Stay tuned for the next scene as we explore the complex interplay between fission and fusion stages in a hydrogen bomb. In the preceding scene, we learned that the fission bomb is the spark that sets off the whole chain reaction in a hydrogen or thermonuclear bomb. Now, let's discuss the critical components that surround the fission bomb in the secondary stage. This secondary stage comprises of hydrogen isotopes, specifically deuterium and tritium. These isotopes are critical as they are the primary fuel for the fusion reaction. But it's not just the hydrogen isotopes that play a pivotal role. Other components, such as the tamper and the pusher, are also crucial. The tamper, usually made from uranium-238 or lead, aids in containing the energy from the fission bomb long enough to increase the pressure and temperature to a level necessary for fusion. The pusher, often constructed from beryllium, acts as a shock absorber, slowing the expansion of the fission bomb and increasing the compression of the fusion fuel. These components work in unison, creating a delicate balance that allows for the extreme conditions necessary for a fusion reaction to occur. The fission bomb, the hydrogen isotopes, the tamper, and the pusher all coalesce to create a scene of immense power, paving the way to the fusion stage. But how exactly does this lead to the fusion and fission stages? Stay tuned as we delve deeper into the complex interplay between these stages in the next scene. The stage is set, the components are in place, but how do we go from a stable assembly of isotopes and metals to a thermonuclear explosion? It all starts with the detonation of the fission bomb, the catalyst for the entire process. When the fission bomb detonates, it releases a tremendous burst of energy, primarily in the form of X-rays. These X-rays serve a crucial role in the fusion process. They rapidly heat and compress the hydrogen isotopes, deuterium and tritium, in the secondary stage. The heat and pressure from the X-rays cause the isotopes to collide at high speeds, overcoming their natural repulsion and forcing them to fuse together. This is not just any collision. It's a collision that occurs under extreme conditions, creating the perfect environment for fusion. This high-speed collision and fusion release a great deal of energy, significantly more than the fission bomb alone. The energy from this fusion reaction further drives the fission in the tamper, creating a chain reaction of fission and fusion. In the next scene, we'll delve deeper into the complex interplay between the fission and fusion stages. So stay tuned as we continue our journey into the heart of a hydrogen bomb. Imagine a dance floor filled with dancers, all moving in rhythm. On this dance floor, we have our main stars, the hydrogen isotopes, deuterium and tritium. The X-rays from the detonation of the fission bomb have heated and compressed them, creating an environment akin to the center of a star. The intense heat and pressure force the deuterium and tritium to overcome their natural repulsion and collide at high speeds. When these isotopes collide, they don't just bounce off each other. Instead, they unite to form a heavier nucleus, helium. This fusion of deuterium and tritium also releases a neutron, along with a significant amount of energy. This energy, in the form of high-speed neutrons, is then absorbed by the tamper, causing it to undergo fission and release even more energy. So in essence, the fusion of deuterium and tritium is not just a simple collision. It's a dance that leads to the creation of a new element, the release of a neutron, and the generation of a tremendous amount of energy, setting the stage for the next round of fission and fusion reactions. In our next scene, we'll delve deeper into these fission and fusion stages. Stay tuned as we continue to explore the complex and fascinating world of hydrogen bombs. As we have seen, the fusion of deuterium and tritium releases a stream of high-speed neutrons. These neutrons, each carrying an enormous amount of energy, zip away from the fusion reaction at the heart of the bomb. But where do they go? What role do they play in this cataclysmic event? The answer lies in the materials surrounding the fusion stage, the tamper and the pusher. These components, often made from uranium-238 or lead, absorb the high-speed neutrons from the fusion reaction. The absorption of these neutrons triggers yet another round of nuclear reactions, known as secondary fission reactions. This is where the true power of a hydrogen bomb lies. Each neutron absorbed by the tamper and pusher can cause the atomic nuclei to split, releasing even more energy in the form of heat and blast waves and more high-speed neutrons. These newly created neutrons can then cause more fission reactions, creating a chain reaction that exponentially amplifies the destructive power of the bomb. The secondary fission stage, therefore, is a crucial factor in the overall yield of a hydrogen bomb, transforming it from a powerful bomb into a weapon of immense devastation. In the next scene, we'll delve deeper into the interplay between these fission and fusion stages, so stay tuned. Now that we've understood the role of secondary fission, let's take a moment to appreciate the magnitude of the energy being released. The fusion and fission reactions are not just two separate entities. Instead, they are intricately intertwined stages, each amplifying the other, leading to an explosion of immense power. The combined energy from the fusion and fission reactions results in an extremely powerful explosion, releasing destructive force, heat, and radiation. This is not just any explosion. This is a nuclear explosion. And it's not just the blast that is devastating. The intense heat can ignite fires many kilometers away, and the radiation can cause immediate and long-term damage to living beings and the environment. The fusion reaction releases high-energy neutrons, which trigger further fission reactions in the tamper and pusher. Each of these fission reactions releases even more neutrons, creating a chain reaction that multiplies the destructive power of the bomb exponentially. What's more, the energy released by these reactions is not just in the form of a devastating blast. The high temperatures generated in the process also produce a brilliant flash of light, so intense that it can cause blindness to those who see it directly. In the next scene, we'll delve deeper into the interplay between these fission and fusion stages, so stay tuned. As the explosion subsides, the immediate aftermath of a hydrogen bomb detonation is nothing short of apocalyptic. The energy released from the reactions forms a rapidly expanding fireball that engulfs everything in its path. The intense blast wave flattens buildings, infrastructure, and natural structures, leaving behind a path of complete devastation. The fireball, reaching temperatures hotter than the sun's surface, emits a blinding flash of light, followed by a thermal pulse that can cause severe burns and ignite fires over a large area. The radiation emitted from the explosion can have both immediate and long-lasting effects, causing sickness, genetic damage, and even death. But the destruction does not end there. The explosion also produces a mushroom cloud, a symbol universally associated with nuclear explosions. This cloud can rise several kilometers into the air, carrying with it radioactive debris that can spread over large areas, causing what's known as nuclear fallout. This fallout can contaminate the environment, water, and food supplies, leading to long-term health and ecological consequences. This scene shows the terrifying destructive power of a hydrogen bomb, a result of the intricate interplay between fission and fusion stages, which we'll delve deeper into in the next scene. The first step in the process involves something called a fission bomb, akin to the atomic bombs used in the mid-20th century. This fission bomb, typically comprised of enriched uranium or plutonium, is the catalyst, the initiator of the ensuing reactions. Next, we have the fusion stage. Here, the fission bomb is surrounded by a secondary stage filled with hydrogen isotopes, specifically deuterium and tritium. Along with these isotopes, there's a tamper and a pusher. The tamper is usually constructed from uranium-238 or lead, while the pusher is often made of beryllium. As the fission bomb detonates, it emits a surge of energy, primarily in the form of X-rays. These X-rays are directed towards the secondary stage, causing the hydrogen isotopes to heat and compress. This high temperature and pressure are the perfect conditions to trigger fusion reactions. During this process, deuterium and tritium nuclei combine to form helium, releasing a neutron and a significant amount of energy. But the process doesn't end here. The neutrons produced during these fusion reactions set off further fission reactions in the surrounding tamper and pusher materials. This secondary fission stage massively amplifies the explosive yield of the bomb. Finally, the combined energy from the fusion and fission reactions results in an incredibly powerful explosion, releasing a destructive force, heat, and radiation. To recap, the hydrogen bomb's process starts with a fission bomb, moves on to a fusion stage involving hydrogen isotopes, then utilizes the energy and X-rays generated to compress and heat these isotopes. This triggers fusion reactions, which in turn set off a secondary fission stage. The culmination of these reactions results in a massive release of energy, heat, and radiation. Understanding the workings of a hydrogen bomb is no small feat. It involves complex physics and intricate sequences. But it's a testament to the power of human ingenuity and a stark reminder of the responsibility that comes with such knowledge. If you found this video insightful, don't forget to subscribe for more intriguing content. Until next time, keep asking questions and seeking answers.